let's go ahead and see what it means to integrate the component of this vector field in the direction of motion around the circle. Let's just postulate a circle of radius 1 centered at the origin, and we'll parameterize this circle in a familiar way as x equals cosine of 2 pi t, y equals sine of 2 pi t, t going from 0 to 1. And what we know in advance we're going to do is we're going to break this circle up into a bunch of little pieces. This little piece here would be associated with the displacement from this point to this point. The function is here. The delta S vector would be from here to here, but we've moved it out here so we can see it. It'd be about like this, and we see that the delta S and the F vector aren't quite exactly perpendicular at on this particular segment, although actually the segment looks like it's pretty close to 45 degrees, and at 45 degrees we would have perpendicular. Let's not worry about that though. Let's go ahead and look at the process. Okay, so we partition our interval 0 to 1, and our partition looks like this, and our sample points in the ith interval are ti star, well, sample points are ti star with ti star in the ith interval. We draw a little bigger picture of what goes on in this integral. We have the function f, and to clarify, this function is going to be evaluated at what? At x, y, z, but x is now a function of t, y is a function of t, and z is a function of t. Now, this circle is of radius 1, and we should probably say in the plane z equals 0, so that wasn't in the preceding clip. We'll add that at this point. So in the plane z equals 0, z is going to be 0. So our sample point ti star is on this circle in the plane z equals 0, therefore the z coordinate evaluated at our sample point is going to be 0. Again, to reiterate, f is evaluated at x, y, z. X, y, z are on this circle, so they're parameterized in terms of t. We have a delta Si, a displacement between the two endpoints of our path. Our path starts at x of ti minus 1, y of ti minus 1, z of ti minus 1. That is, the ith interval runs from ti minus 1 to ti, so that our sample point is somewhere between x of ti minus 1, y of ti minus 1, z of ti minus 1, and the terminal point of our interval, x of ti, y of ti, z of ti. So we have a delta Si between those two endpoints. We have the function, and we're trying to find the component of this function in the direction of delta Si. Now, the component of our vector function f in the direction of delta Si is just the projection of this function onto the direction delta Si. So what we're doing then is integrating that projection times our delta Si. The projection could be positive or negative, depending on whether this function has a component in the direction of delta Si, or if the f was back in this direction, a component in the direction opposite delta Si. The projection takes care of that. Projections, of course, done with the dot product and so forth. So when we do the projection times the magnitude of the interval, the magnitude of the interval is always going to be positive, but the projection could be positive or negative according to whether the function is kind of pushing in the direction of the displacement or opposite the direction of the displacement.